Hi, and welcome to Section 6 of the Micromachining Lab module. In this section, I will be talking to you about surface roughness and its importance in production environments. Just as toolware, this is an important section, and understanding what surface roughness is, how it happens, and the role it plays in machining will help you appreciate many of the products you use in everyday life. Reduction in surface roughness is what allows for the smooth surfaces we don't typically think about. After this section, you should have a good comprehension on what surface roughness is, its importance in machining and micromachining operations, and how it's measured and analyzed. There are machine parameters as well as relationships between tool and workpiece material that influence surface roughness, and will be presented here to highlight where improvements can be made for the production of high-quality parts. Surface roughness, or surface texture, is the nature of a surface and is defined by deviations of a surface from a perfectly flat, ideal plane. What if every door handle you used had sharp edges or was rough to the touch? It would be difficult to function properly. Along that same thought process, think of a needle used in a medical procedure. If it was too rough, it could cause patient discomfort and increased recovery time. Manufacturing processes such as milling and turning produce a surface texture, and the quality of that surface finish is highly influenced by the interaction between the cutter edge and the microstructure of the material being cut. There is a number of industries that have critical tolerances for roughness, especially the consumer product, medical, and aerospace industries. Surface roughness is defined as the quantitative measure of the texture of a machined feature based on a statistical deviation of peaks and valleys about a midplane. Here we can see differences in how roughness is categorized. As you can see from the graphic, the goal is to achieve a flat and smooth surface. However, design requirements can prioritize different aspects such as smoothness and flatness depending on the application. Similar to toolware, the spindle speed, depth of cut, and feed rate machine parameters are the primary influence of surface roughness on a part. As you might imagine, if you are cutting across a surface very fast, there is potential for the cutter to not fully remove all material, resulting in lower quality roughness by causing greater variations in the peak and valley deviations from the midplane. Surface roughness can be comprised of up to 4 factors: lay, waviness, roughness, and flaws. Lay refers to the orientation of the predominant surface pattern and is normal to the feed direction. Waviness is the measure of large-scale surface irregularities in the feed direction, whereas roughness is the measure of the finer surface irregularities in the height of the workpiece along the z-axis. Finally, flaws can occur if there is a non-uniformity in the workpiece material or if there is an error in the machining that causes damage to the surface. We will be primarily focusing on the analysis of roughness in this module. Similar to Section 5, we will again be using the Digital Microscope and Image software to measure the depth and width of the slots in the workpiece material. Relevant images of the slots will be supplied to you so that you can analyze and draw conclusions about the effect different process parameters have on the size of the slots produced. To generate an approximation of the surface roughness, you will be measuring the values of the peaks and valleys that were generated using a profilometer of the floor of the slots. The numeric approximations are listed on this slide, and there's also a surface roughness calculator to aid you in these calculations. Please refer to the Section 6 Image procedure in the folder for steps on how to measure the dimensions and features previously described, mainly slot width, slot depth, and surface roughness approximations from the profilometer data.